right. From our first practice problem, the first thing we are asked to do is identify on a structure if you would like to. First thing we're asked to do is identify the acidic proton. Seeing as you can only see one proton, where is it? The H on the right. The H is the proton. Okay? It has an acidic proton, so it's an acid. It's okay. That being said, the next thing to do is to write the reaction. Now what I'm going to do is I'm going to abbreviate this like this. That's the name of the molecule with the proton attached to it. So just imagine I drew the whole thing again. Does that make sense? Okay. What do we add an acid to? Water. When it does that, the proton is going to go and join our water molecule, give us hydronium and niacin without a proton. Okay. Next thing it says is we're given a 0.02 molar solution of niacin and a pH of 3.26. The question is, what is Ka?
That's a good question.
Where does the 0.020 go? That's my initial concentration of my niacin, correct? You agree? We do not have water. What about these two? They are zeros. Next thing I'm given is a pH. And what did we say about pHs and equilibrium?
Oh, they are.
So if we can get the concentration of H, that concentration is our concentration of H at equilibrium. So these are equilibrium indicators. pH is just an abbreviated way of giving us the concentration of H. So let's get the concentration of H from our pH. Yes?
It's really 5.5 times 10 to the -4.
Holy crap, that was quick. You said 5.5?
Yeah, because it's 5.49.
It's fine. 5.5. That's what I've got. I've got 5.49, but yeah, it's fine. That number goes where on here? Equilibrium, H3O plus.
That means X.
That means that that's our X, correct? Because we know this, we know that the change in X must be the 5.5 times 10 to the -4. 0 plus a number made this number, so it must be the X. Over here, we have to subtract that X. When we do so, we get...
0.02.
No.
0.
I got that.
Yeah, 0.01945.
It's very small, a difference, but it is a difference when you plug it into Ka.
Yeah, if you're on
Yes.
Yeah, but if you're on the exact same thing.
Will the products always have the exact? In this particular case, yes, and I'm going to go with most of the time, yes. Okay? Yes.
This is just a calculator question. So when I'm putting it in there, I got assigned the application number. Is that like, and it doesn't look right. I got 1.1 times 10 to the -4.
For what?
For when I multiply, oh, I'm supposed to never mind.
Have I not done the next? I haven't done the next step yet. Okay. All right. Next is Ka, right? Plug them in. didn't write a k expression, but what would the k expression look like before we plug numbers in?
H plus times niacin.
Minus, right? So the base form
Over niacin minus H. Oh, wait.
over niacin, yeah, so it's niacin with the H attached, right? Yes.
That second 5.5, is that supposed to be a 4 or is it, okay, I didn't know if you changed it for some reason.
My hand slipped.
No, it's okay.
Yeah.
I just wanted to.
1.6 times 10 to the negative 5th.
I think I got this. But I digress. Yes.
I had like 1 point, like a 5, 6, is that also?
We're in the neighborhood. Okay. Are we done? Did we do what we were asked to do?
Yes.
We got the K, right? All right, let's move on. Next up, write the reaction, the same reaction from number 1 for number 2. So we're using the same exact niacin reaction. The question says the Ka for niacin is supposed to be 1.5 times 10 to the negative 5th. So I'm going to erase some of my stuff. I'm going to leave some of it since I'm using the same reaction. It says the Ka is supposed to be 1.5 times 10 to the negative 5th. My question here is, what is the pH? So that's my final goal. Of a 0.1 molar solution, 0.01 molar solution of niacin. All right, let's fill the rest of it in, starting with the initial. What other information was I given?
Nothing.
Nothing. So what does that mean?
0.
Zeros across the board. We don't care about the liquid water. All right, what's next? In the change column on the left,
Negative X.
minus X. So we're going to use our K expression, and we're going to plug our numbers in, or our expression, or our X's, I guess. We're going to set it equal to what the K is supposed to be, and we're going to solve for X. Get it into the quadratic, and then I'll give you what X is.
Is it x squared equals or x squared plus?
There's my quadratic. My X value came out to be 3.86 times 10 to the negative 4th. Yes. What does that X mean? That means this, right? Don't forget to do the end of the problem. Solving the quadratic does not end the problem. Solving the quadratic gives you the concentration of H, which then you need to get pH for. Correct? So how do I get pH with that number?
Negative log.
So I'm going to do the negative log of that number. Since it's an acid, we're hoping for a number below 7. What'd you get?
2.41.
From our previous problem, the pH was 3.26 and 0.02 molar. This problem, it says 0.01 molar. So we halved the concentration, and our pH only went up by 0.2, I guess, units, if you will, on the pH scale. So that should give you an indication of the pH scale not being a good indicator of strength. It just kind of gives you an idea of where you're at as far as compared to other acids. Comparison tool, not absolute scale. Okay. Next up is going to be calculating the pH of something that's a polyprotic acid. And all we're going to do is remember what we said about our polyprotic acids. Do we care about the second Ka? No. We only care about Ka1 in a polyprotic acid. Can I erase? So again, set it all up. The first question says, what's the reaction that removes the first proton of this acid? So you're going to write the acid equation. The acid that we're starting with is H2CO3. If we're saying that's the acid, we're going to add it to what? Water. What does that make water? Acid or base? Must be the base. That acid's going to give up a proton to the water, correct? And you're going to get this. Do you agree? What else? HCO3 minus. You removed a proton. So it became less positive. It also says, what's the expression for Ka1? Well, that's the number. Okay, what's the expression using the balanced equation?
HCO3 and then H plus over H2CO3.
All over the acid. Nice. So that was A. B says, why can we ignore the removal of the second proton? And if we look at the Ka values of Ka1 and Ka2, Ka2 is much larger as far as the number, so a much weaker acid compared to Ka1. Okay?
Are we trying to make strong acids like preferably? Or is it, we just always choose the smaller number?
You would always choose the Ka that is stronger, so the smaller one.
Okay.
Ma'am?
So for B, I think we just answered this, but why would it be removal of this?
Because this second one, the second proton, in order to remove it, you would need more of the conjugate acid or the conjugate base that actually gets produced. It's not likely to happen, is basically the end of the question here. Oh gosh, yes.
So for this problem, would H3O plus be the conjugate acid and HCO3 minus be the conjugate base?
Correct. Yes,
So you said for the polyprotic acid, we ignore Ka2?
correct. We only use Ka1 when we're doing these problems.
Okay.
We basically assume the pH only depends on Ka1.
What if it wasn't polyprotic, then we consider it a mole?
Well, if it wasn't polyprotic, you would only have one Ka value.
Okay.
Does that make sense?
Yeah.
Okay.
I'm confused on where the formula came from. Is this different than?
We wrote that out. The formula they gave you was the creation of that acid.
Oh,
Oh, yeah, that's what I was asking.
Yeah. Molly.
okay.
So you'll never like in theory like use K. Like,
Say again?
Like K2 is always gonna be like extra information.
Correct.
Okay.
Ka2 is usually given just so that you can double check. They should be at least 3 orders of magnitude apart in order for you to be able to ignore them. And we're not going to talk about how to use them. So for the most part, we will ignore them. Okay. All right. So here's our expression. Here's our equation. Next thing to do is to actually solve the problem we were given, which says, what is the pH of a solution of this concentration of H2CO3? So we're going to make an ice table. What are we going to put in the ice table?
Not water.
Definitely not water. It's always nice to be able to cross something off.
0.0037.
Here? Yep. That's our initial concentration of our acid. What about over here? Zeros. In the change column?
Minus X.
Minus X plus X. Yep. Plug it in. Oops, 2 zeros. I don't remember doing all these quadratic equations yesterday, but it's the end of the day. All right, what's next? Set it equal to the Ka we were given. Solve. Do you need to see me give you the quadratic, or can I just give you the x values? X equals, I got 4.45 times 10 to the negative fifth. Which gives us concentration of H3O plus at equilibrium. So now we can calculate pH. My pH came out to be 4.35. So same as the previous problem, all we did was say Ka2 is one we can ignore and write an acid-base equation. All right. Next up is the base version. Oh, we did this one in lecture. Yeah, I'm not going to do this one. We just did this in lecture. 0.15 molar solution of NH3 with a Kb. Calculate the OH minus concentration, so you don't even have to give me a pH or a POH. You're just asked to find OH minus, which means the equilibrium concentration. So before I skip it completely, what's the reaction you should write for NH3 being the base?
H3 plus H2O.
Right? NH3 plus H2O makes
H4.
NH4 plus and
Oh,
OH minus because it's a base. All right. You can do that one on your own, or you can look back at your notes. I'm pretty sure it was the exact same concentration too. We just did it in lecture. I didn't realize that. All right. Last thing is determining the concentration of a salt, which is really just a fancy version of a Kb. Okay? So we're given information about a salt, sodium hypochlorite, that's going to dissolve and become this ClO minus ion. ClO minus being a base. Okay? First thing we're asked to do is write the expression. Write the reaction. Treat the ion, the anion of a salt, as if it were the conjugate base of a weak acid, aka a base. What do we do? Let's add water.
Just add water.
What are we gonna form? HClO. Since we're adding a proton to it, doesn't it become neutral?
Oh, yeah.
Becomes neutral. And what's left over?
OH minus.
And OH minus. All right, what's the equilibrium expression gonna look like?
HCOO,
So HClO
OH minus,
times OH minus all over
COO.
ClO minus. Okay, set up our ice table. Next up, put in information we know. So it says the pH of the solution is 10.5. And we were given the Kb is this guy. Okay.
Is that to the negative?
Yes. Is this going to help me in the way that it is currently written up here somehow?
Yeah. Well, not up there,
Are you
but
sure?
down there.
So I guess the question is, what can I do with pH? I can solve for what?
Concentration.
Concentration of H plus. Do I have concentration of H plus somewhere?
No.
No. So that's not really that helpful.
Oh.
Would it be more helpful if it was a POH?
Yeah.
Yeah. So let's get POH. Yep. Now that I have POH, what can I do with that?
Concentration of OH.
Let's get the concentration of OH minus, because once I have the concentration of OH minus, I know what it is at equilibrium. I got,
3.16 times 10 to the negative 4.
yeah. In this particular reaction, I'm looking for the concentration of ClO minus, meaning I'm looking for this. We know this doesn't matter. We know that likely this started at 0, this too, and we know that it became
So the value of X.
so now we know the value of X. Now what I'm going to do is I'm going to remove the X's because they don't really mean anything, right? And there's a reason. Because that's what goes here. My X is really my unknown up here. So some number minus that equilibrium concentration that some number is the concentration I started with. We've never quite done one like this before, but the principles all apply. So now we have an equilibrium expression. What do? Plug it into KB, set it equal to the 3.3 times 10 to the negative 7th, solve for the X. We understand why it's squared? Because they're the same at equilibrium? Multiply it over. Not quite. Bless you. This is what I got. It's not wrong. Because you square this, it becomes that. Move that over, that becomes that. Yeah,
Okay, thank you, sorry.
that's where I'm at.
Okay.
So now, I'm just gonna add. This number is small compared to the 10 to the negative 10th. Doesn't even affect that number. Divide both sides by the number in front of x. That's what I got. Yeah.
So the number on the right side, so you have your, what you set KB equal to, like your expression, and then.
3.3 times 10 to the negative 7, yep.
Yeah, and then equals the 1.4 times 10 to the negative, what's the number to the left, all the way to the right?
1.04 times 10 to the negative 10. I added it to both sides. I moved it.
Oh,
Is this one you're talking about?
No, above that, what you added it to.
Oh, I said it equal to 1 times 10 to the negative 7, because that's this squared.
Okay, I just didn't see it.
It's okay. All right, start working on those practice problems. Yeah.
So, CLO minus 5.
No, you could do that. Absolutely. And divide by KB. Is that what you're saying?
Yeah.
Yeah, you could absolutely
And
do
just
that.
add 3.1.
Yes. You can do that. You should get the same number I got.
Yeah, I got
Like close.
yeah, like oh different.
Yes. Squared. Okay. Oh, the 7?
It was good.
You're good. Start working on your practice problems, please.
Are these due tonight?
Yes.
Yeah, I think Cal.
Yes.
Did you finish your binder?
I was gonna say, I was really stressed.